Hello everybody, welcome to my homework 4 default homework where I am going to be doing part 1 in this video today. I will be implementing the NRT activity coefficient model via Python loops, einsum, and matrix vector multiplications. Then I will compare the results of the 3 implementations for a mixture of methanol, ethanol, and water at 300 degrees Kelvin, and it's equimolar. So, this is, leaves us with a couple natural questions. Looks like there's going to be 3 parts to this. I need to somehow implement this activity coefficient with Python loops, einsum, and matrix vector multiplications. And then I'll compare them all. That'll be pretty simple. It gives us some ambient conditions, and with all that, I think I'm about ready to start talking about, this a little bit. So let's start out really quickly by talking about Raoult's law. Raoult's law is, it has to do with vapor-liquid equilibrium. And it says that when you have a mixture of a certain number of fluids, or a certain number of liquids, if you have like a liquid-vapor equilibrium made up of some components which can go I through, however many, that the gas phase mole fraction is going to be times the fugacity times the pressure is going to equal the liquid phase mole fraction times the activity coefficient. This is I think a gamma times the saturation pressure. The activity coefficient, I think that's a gamma. I'm not quite certain actually. I don't really know my Greek letters. I'm not in Greek life or anything like that, so I don't really know any of that stuff. But anyway, there is a general equation you can use to sort of describe, to figure out what these activity coefficients are. And of course, these activity coefficients are going to be determined by what the mixture is. So in an ethanol water mixture, the activity coefficient for each component, whether it be methanol, ethanol, or water, is going to be different. Or is going to be like a certain value at a certain temperature. And so there's this NRTL model for deriving what the activity coefficient should be. And so this says the natural log of the activity coefficient is equal to all these annoying summations. And then we can get this g from the exponential of an alpha times tau. Tau can be calculated using all of these. And this alpha value for 2 components, and these values of A, B, C, D, these constants down here, these are all constants that are sort of like natural physical properties of the the mixture, and so those will be importing from a function my professor wrote, or from a Python document. I don't really know what to call exactly. And so we'll sort of use all of that to figure out the activity coefficients of all these. So let me go ahead and go to my homework 4 real quick, and let's take a look at this imports and installs real quick. I'm importing a GitHub file, and then using this import notebook, I'm installing this import notebook library. And then from that library, I'm going to import notebook, and then use that to import ch4, which is something my professor wrote that has this, for now, all we need is the props definition in it. So, well, props, I guess it's not a definition, it's a function, I believe, or maybe it's an attribute. I honestly don't really know all those words. It's something I'm going to use to get the properties of certain mixtures, or of certain components. So I will then use numpy for this, and there's a few other imports that I just have just to be able to use it later. But for now, that's enough importing. Let me really quickly explain the code, and then I'll clear it all out, and then I will start back from the beginning. So I want to define a function of the activity, and I'll start off by doing it based on the loops using Python loops. And I'm going to go through and loop through and do the math to sort of calculate all this out. And I will return 3 activity coefficients, and then there's some properties, some mole fractions, and temperatures. But with that, let me go ahead and maybe delete this, and I'll just leave this P, X, and T. So if I were to go ahead and restart the runtime, yes, I do want to restart the runtime. It'll take a second to do that. As you can see, I copied some of this information into here, just so it was easier to reference as I was going through. Did I get this to rerun? Runtime. I think I hit restart and run all, didn't I? Yeah, I'll just hit that again. I might have not hit the button correctly. I don't know. I should have gotten results here. So, here's what this P is saying. P is a variable that contains all the properties of methanol, ethanol, and water. And that's, this props is something that I imported from my professor's Python file. And so then X is going to be the liquid mole fractions of the three components each respectively. So that would just be, because it's equimolar, it would be 1/3 methanol, 1/3 ethanol, and then 1/3 water. And then the temperature is just going to be 300 degrees Kelvin. And that's all, specified right here. So with that all in mind, let me go ahead and maybe add another code cell. Let's go ahead and start defining this function. So I will define the activity loops. For some reason it already has that filled in. Activity loops, and I will need to give this activity loops a mole fraction of the components, and then also a temperature of the mixture. And then I'll just not even put in a P. We'll just leave P out of it for now. So I have these activity loops. What do I need to do? Well, I need to go through and calculate all the stuff in these summations and multiplications and all that. But before I need to do that, I need to get values for tau and then values for g. So how am I going to go about doing that? Well, tau is given right here. So you can see that tau is going to be the constant A plus B over the temperature plus C plus D, yada, yada, yada. For these three components, A, C, and D are all 0. So tau is just going to be B divided by T for all the components. If I can just go through and say tau is going to equal the properties, NRTL, and then you can see I can import this constant B. So the activity coefficient B constant of whatever P, so that would be methanol, ethanol, water. So tau is going to be that divided by the temperature specified. Sounds pretty straightforward. Then to get this G value, I just want to take the exponential, so NP times, and then this alpha is another constant, but I can just go ahead and, if I can spell, alpha, yep. So the properties of the NRTL coefficient alpha, and that needs to be negative actually, times tau, which I already calculated down here. So an important note, and that's featured down here, the activity or the alpha value of, say, water and methanol is the same as the activity value of methanol and water. So the activity coefficient, or this alpha, not activity coefficient, but the alpha is going to be the same both ways. The B and all these other constants do not necessarily work that way. So that's an important distinction, or else, and that's why it's important to keep straight these iterative variables up here and make sure that I don't lose track of those and make sure I sort of do those in the right order. So with that all in mind, I can start maybe looping through, and I'll need to iterate through some I, and then I'll need to start working with all these summations. So I think to start out with, I'll go ahead and break down this first term up here. I'll call this first term part 1, and I'll break it down into term 1 on top and then term 2 on the bottom, and that'll become important later. So let's see, on top I need to sum up the values of the mole fraction times the tau times the g. The mole fraction will just be for each component. The tau and the g I need to iterate through each component for the tau for the component I'm looking for, the component that I'm currently trying to judge, and then the actual the component I'm trying to refer it to. So this would be like saying it's the mole. If I'm trying to find the activity of water, this would maybe be the mole fraction of, say, we'd start out with water, times the tau of water with itself, which is just 0, times the Gibbs, the G. I don't know what G is actually. I should maybe have figured that out before I started this video. But anyway, I'm trying to, I need to keep these iterative things straight and have a basic understanding of what they mean. So I can go ahead and, yeah, I need to figure out how long to loop all these variables for. So whenever I'm looking at j to n, I'm going to start from 0, but where do I go to? Well, in this case, since I have 3 components, I'm always going to want to iterate 3. And I think the best way to do that, that just works permanently, would just be to say x dot size, that nothing should be in parentheses. And then I'll say that n is equal to x dot size. And then whenever I'm iterating through, I'll go ahead and say for I in n. No, a range with the length of n. That is the correct way to do it. But then something I realized that I kind of meant to do was, what do I want to return from this function? Well, I want to return an array of the activity coefficients. So I'll maybe call that ACT, just short for activity, or advanced collegiate test or something. I forget what ACT actually stands for, like the test everyone takes in high school. At least everyone in the Midwest takes. On the East Coast, they take the SAT, but in the Midwest and sort of Middle America, the ACT rules. So I grew up, in Cincinnati area, so I took the ACT. But anyway, I've got this tau g n. What do I want to do from here? Well, let me go ahead and maybe define act as just just a bunch of zeros. So zeros like, and then it'll just be like x. So the activity coefficient is just going to be an array of, in this case, three values, and those are the 3 activity coefficients, and that's what I'm going to return at the end of the function. So that's just something. I'm going to have a few other sort of blank variables like this, but for now, let's just continue on with these ranges. So for I in range n, I want to take the summation of all this up here. So I can maybe come down here and say that term 1, this top term, is going to be equal to 0. And then, nope, it's going to add on something that I didn't want for some reason. I don't know why. And then I can say for j in a range, I can't spell, because of course I can't, in a range n. So for j in range n, term 1 is just going to equal itself plus, and that's what this term means. It just means add itself, and then it's going to equal, it's just going to equal itself plus this. So the x evaluated at j, tau evaluated at ji, and then g at ji, or the g term in this g array. So I would say that x evaluated at j times g, or no, I just want to make sure I do it in order. It's tau second, even though that's not like super duper important. Tau evaluated at ij, if I did it correctly. No, it's ji. That is important because those are like the dimensions in the array I'm looking for the value from. So if I get those reversed, then it's going to mess up my answer. And then times g evaluated at the similar ji. So I need to actually say term 1 here. But now that I have this term 1, so this top term defined, I can go ahead and define the bottom term. So we'll say that term 2 is also going to be 0. And then for k in range, and it doesn't matter what iterative variable I use here, but the problem statement uses k, so I'm just going to go ahead and use k. I can say that term 2 is just going to equal itself plus, let's see, what is this one? xk times gki. So that would just be the mole fraction of component k times the g of component k and component I. And let me make sure I did that in order. I did. Sweet. Sweet. So now if I wanted to get maybe the first part, I could just say that part 1 is just term 1 divided by term, nope, that's not what I wanted. I wanted to copy it and then paste it in here. So term 1 divided by part 2. Now, there's kind of a flaw in this, right? Because I'm iterating, I'm going to keep changing part 1 so that it's not, part 1 is just a variable right now, it's not an array. So I actually need to, instead of just defining part 1 as term 1 over part 2, I need to say part 1 for component I is term 1 divided by term 2. And then I need to actually go in and do something with, like what I did up here, and say that part 1 is going to be zeros shaped like X. So I can go ahead and run that, and let me maybe add in a new code cell. And I'll go in up here, and I will just copy this down. I'll say that the activity loops evaluate at X and T, which I have already done down here. So the activity coefficient according to the loops is going to be 0, 0, and 0. That's because the activity coefficient is just returning a blank array. But if I go ahead and maybe say, well, I want to print part 1, which I didn't spell correctly, because why would I spell it correctly? And I'll go ahead and move that outside of it, and then I will just go ahead and comment out that return. And let's see what I get. Yeah, sweet. So this is saying for part 1 of the activity coefficient calculation, I get the values of, so for this part 1 up here, I get the values of this for methanol, this for ethanol, and this for water. But of course, now I need to move on to part 2. But because the way I set up part 1, part 2 shouldn't necessarily take as much math. Because if you notice, look at this, like, what I defined as part 1, well, that's the same thing as this, just with some different iterating variables. Instead of iterating relative to j and I, I'm iterating relative to m and j. And then I need to subtract the tau ij, and then you can see this term is sort of repeated over in this area. So, there's a way for me to sort of copy what I've already done in order to solve this part 2. So let me go ahead and start a new loop for part 2. So for I in range of n, what do I need to do? Well, I need to, let's start out by doing this part in parentheses over here. So for I in range n, I actually want to go in and say for j in a range n, I want to iterate relative to j within iterating relative to I. I'm going to say that I need to find tau evaluated at, I think it's I comma j. I have to keep scrolling up and down. And I'm realizing that a lot of what I'm writing is probably getting cut off because of my camera's angle, so that kind of sucks. But, let's see. It needs to be I comma j, correct. Yes, sweet. So tau of I comma j, and then minus, well, I'm just going to subtract off what I did up here in part 1, but part 1 evaluated at I. So for every value of I, I'm going to get a certain value of part 1. Because, you look up here, and, this part I'm iterating relative to j and I. This part I'm iterating relative to m, or k, and j. So I needs to become j, and then m and k, or what I have here is j, needs to become m and k. And then I, of course, need to subtract off this tau ij. So with that, I have this term in parentheses worked out, but I need to go through and multiply in the mole fraction of component j times the g of I and j. So I need to take that and multiply in the mole fraction of component j times the g of component I and j. I think. Let me check that again. I and j, and I know I put a wrong parentheses in there, and I know you probably can't see it, it's all getting cut off anyway, so what's the point in being so, I don't know, anal about it, but hopefully that is visible. I think it's visible, like, down, I think right here my mouse is, like, sort of getting on and off screen, so, I don't know, or my cursor is, rather. So is it ij? That's what I hold, straight out, yeah, it's ij. So, sweet, this is sort of the top part of that term. And I'll go ahead and maybe put some spaces in here just to break it up a little bit. And now I need to take that whole thing, and I actually don't really need to put it in parentheses, I won't do that. And then divide this whole thing by this term right here, where I'm summing up xk times g kj. Now, one thing that I probably, pick up on right here is that, sorry, that's probably like the 100th time I said so kind of cringe, honestly. I'm doing it again. I lost my train of thought, and now I'm just saying all the time. This is great. I love that. Okay. Let me recollect my thoughts for a second. This right here is the same as this right here. And so this is what I defined earlier as term 2 as a part of part 1. So let me go ahead in here, and maybe I'll go ahead and say that before I go ahead and divide term 2, let me make a new variable. I'll call it term 2 save. And then term 2 save is just going to be equal to term 2, but not term 2 save as a whole, term 2 save evaluated at I for, as we're iterating through. That, of course, means I need to go up and create another sort of blank variable for it, so that way NumPy understands what I'm working with, and that'll just be zeros like x. So now I have a term 2 saved over here. So now I can just divide that by term 2 save evaluated at I, and I screwed that up. But yeah, term 2 save evaluated at I, and yeah, so I'm looking pretty good there overall. I have this x. Now I need to go ahead and define this as something. Well, this is just the whole part 2 of the problem as I described it earlier. So I can go ahead and maybe just say that this is equal to part 2 I, right? It's not part 2 as a whole, it's part 2I. And then part 2I actually needs to be this plus itself, similar to how I iterated through sort of adding things up on itself before. So I can go ahead and create another sort of dummy variable isn't the right word, but just another sort of blank variable to make sure it understands that this is an array. And now with that, I have gone through and I have this part 1 all summed up. I have this part 2 all summed up. I can go ahead and add these together, right? So I can just say that the ACT is going to be equal to part 1 plus part 2. And then on top of that, I need to say that the ACT is actually a NumPy exponential of itself. Because, if you think back to this problem up here, this whole summation isn't giving you the activity coefficient, it's giving you the natural log of the activity coefficient. So I use an exponential to cancel out the natural log. With that, let me go ahead and run this. No errors, that's a good sign. And run this. And I don't get the values that I really wanted to be getting. That is kind of unfortunate. So, yeah, okay, first things first, I left a print in there. That's not correct. I can go ahead and run that again, and I get answers that these numbers make sense, right, for the activity coefficients. They're all, sort of they're greater than 0, they're not negative, lower than 2. But these, I've seen the numbers when I was practicing it, and I know these aren't the correct numbers. So let me think through this for a second. Did I set this up right here correctly with I and j? I think maybe, let's see, it is xj times gij divided by term 2 save. I think that's term 2 save evaluated at j. Let me see. I think that was... Nope, that's not the issue. Well, okay. Well, I've got all this. Part 1 seems to be okay. Oh, I think that's part 1 evaluated. Yeah, I need to turn I into j there. So I think that part 1 needs to be evaluated at I and j. And then I think maybe tau... No, I think tau is okay how it is, but I think this part 1 needs to be evaluated at j. Anyway, let me take a second and review my notes and see what I did wrong, and I'll get back to you on the other side. Hey everybody, I'm back with sort of another part of this einsum video, or this homework 4 video. This time I'm going to be going through the einsum a little bit. Last time when I left off, I was having some problems with the loops. I believe the issue I was having was I was incrementing this part 1 and this term 2 save wrong. So that was sort of the error there. But when you actually run the thing, you will get that the activity loops defined at a certain mole fraction and a certain temperature is just going to be, I guess for methanol, ethanol, and water, it's going to be 0.99, 1.14, and then 1.61 respectively at these conditions. So with that in mind, let's go ahead and redo this exact same thing, but this time in terms, or not in terms, but using einsum. So I'll go ahead and maybe copy this. I really like to copy and paste rather than actually writing things out. But yeah, we'll define a new function of the activity coefficients calculated using einsum. We'll give it a mole fraction of the coefficients, a t, and then of course it will be about whatever p is, which is the properties I defined below. So all that's already been defined, already been run. Yeah, so calculating tau and g is going to be the same. It's going to be the same thing as when we just loop through it. But this time I'm going to use something called einsum. So this is the NumPy reference page about einsum. Evaluates the Einstein summation convention on the operands. It has some other stuff about explicit. Basically, this is a NumPy function. We're going to pass into it these subscripts, which is some text that tells it how to increment through a matrix, and then the actual matrices. That's what these operands are. And then everything else, I think I'll leave alone for now. So, yeah, sweet. But what is einsum? Well, let's take a look at maybe this first summation, what I defined as term 1 earlier. So this is saying that I want to go from j all the way through whatever the highest value of j is, and for every value of, or for each component I, this term is going to be the mole fraction of a component relative, a different component of a component times the tau of 2 of the components times g of 2 of the components. And then you're going to take all those numbers, so those 3 numbers you calculated for the 3 different values of j, and you're going to sum it all up. And that's going to be like what this term is up here. And so that's what we went through and did in the loops down here. Now, a potential way to simplify this would be to have a built-in function that can take a bunch of matrices, multiply them together, and then sum it up along some axes. And then summing it up along that axis would allow you to what's the right word for it? It would allow you to calculate this value a lot simpler. So that's actually exactly what einsum does. So I can go ahead and I can maybe say an np.einsum, and I'll go ahead and maybe take the numpy einsum of go ahead and define the matrices first. So what are the 2 matrices I want to multiply together here? Well, you could say, well, in this term 1, there are 3 matrices, but actually, you look at the incrementing of tau and g, those are 2 matrices that are both 3 by 3s, because I and j both have 3 values. So we can actually multiply those together and just do a direct matrix multiplication, just multiplying each value by the other one. But then this xj is a 1 by 3 matrix, or an array, I guess. If a one-dimensional matrix is an array, I think. I'm honestly not certain. I didn't take linear algebra. But I think that's the way it works. So I'm going to have to take this x incremented by j and then multiply it by tau ji and gji. So let me go ahead and maybe say that my first matrix is x, my second matrix is tau times g. But then before I define that, I need to go through and give it this string. And this string is basically going to tell the einsum summation to take my first array and go through an increment of j, or go through a j axes, and then my second array has axes of j and I, so it's 2 axes, and then I want to return it summed up along the I-axis. So the way you do that is my x is in terms of j. My tau g, this is one matrix right now. This tau g is just going to be in terms of ij, or axis I and an axis j. No, it's ji. It's still important to get those axes in the right order. And then I want to turn that into, and I just click colon what I meant to click in, and then I use this little arrow thing. I want to have that in terms, I want to sum along the lines of the I-axes, because that's the actual activity coefficient. So I want it for each activity coefficient. So that sort of turns it into being along the y-axis. And then I can go ahead and say, well, that's just term 1 to put it in the same notation I used on the last problem. Similarly, for term 2, I can go ahead and take the NP einsum of something pretty similar. So I'll just copy paste it and make some changes. This time I'll put it in terms of k and ki, and then only my two matrices are just x and g. So it would be k and ki, and then g. Right? Just got a text. Let me mute my phone real quick so that way I'm not... It's probably about a project. I have a bunch of people in my group and I are all working on some stuff, but I gotta get this done first. So now we have term 1 and term 2. Well, I can go ahead and just keep in the same notation as before. That's just part 1. So term 1 divided by term 2. So then maybe I'll go ahead and print this part 1. And I misspelled print because of course I did. That's awesome. And then let me return. Actually, I won't return anything for now. Let's just run this function and see what we get. Because if this is right, I should get the same thing for part 1 that I was getting before with the loops. So if I go ahead and run this, see what I get. It prints off these three values, and I recall earlier when I ran this loops thing, that was the same as this part 1. In fact, let me go ahead and do this again. I'll say the activity loops, and you see this is from that print that I just uncommented, and it is the same as up here. So awesome. That's what I'm looking to have happen. Let me go ahead and comment this one back out. It's hard to find some of those weird keys, and then I'll comment this back out. And then I'll close this loops chapter. And yeah, sweet. So now I want to go ahead and calculate part 2, which would just be this second term that's added on over here. So let's use a similar methodology to what I did before. Let's go ahead and try to simplify this part in parentheses over here. So we've got this tau ij, which is going to be a three-dimensional matrix, or it's going to be a 3 by 3 matrix, minus this big term right here. Well, this is the same as part 1, and we know that this is going to be a 1 by 3 matrix. So somehow we're going to need to broadcast this so that it can fit into, or it can be subtracted correctly. So what I'll go ahead and say is that I'm going to take tau, if I could spell, tau, tua, that's funny, tua, and then I want to subtract part 1. So part 1. Now, of course, I can't just subtract part 1 because of the difference in dimensions. So I need to say I want to take nothing along the first axis and then all the values along the other axis. And multiply those, or I need to sum up all the values along those axes. I need to broadcast it along the first axis, or broadcast it along the second axis. I think that's what this is. I think that's the right way to say what I'm trying to do here. So then, once I kind of have this term calculated, but what do I actually need to do overall in here? I need to work in another einsum. And so you see down here, you've got this term, this summation down here. That's going to be the same thing, just with some different names of the axes as term 2, right? So we got term 2 here. We have a duplicate of term 2 over here, and this is just end up going to be this is going to end up being, yeah, 3 values. Yeah, it should end up being 3 values because of it should be on the j-axis. So we could copy that over, but then we have actually the main sort of Einstein summation we need to do. which is going to be an x matrix, which is a 3 by 1 in the j axis, multiplied by everything else over here. So it'd be this g in the I and j axis, so a 3 by 3, multiplied by this, a 3 by 3, multiplied by, or divided by this, a 1 by 3, but we'll have to broadcast this to make it fit. So with that in mind, let me start maybe a new einsum. I'll say that NP, I can't type, einsum is just going to have some, it's going to have, some, what's the word? It's going to have some letters. Letters, that's not what I'm looking to say here. It's going to have an 3 values, and then it's going to have 3 values. What am I even trying to say here? It's going to be in the j-axis, and then g is going to be in the ij-axis, but then we want to return it in the I-axis, because I is the actual activity coefficients. So that's pretty straightforward, although after I said it, I forgot it. So it's like this, but I need to switch the j and the I think. So I think I need to go from j to ij, and then return it in I. And then I need to have an x, and then I need to have a g multiplied by this big part in parentheses right here, and then dividing it by term 2. Now, of course, I can't just use term 2 in and of itself. I need to broadcast it along the second axis, similar to what I did for part 1. And that's just because this is a 1 by 3, this is a 3 by 3, this is a 3 by 3, so I need to broadcast this so that it multiplies out by the whole 3 by 3 matrices. So with that, I think that should be good for part 2. I can go ahead and say that the activity coefficients are just going to be part 1 plus part 2, and then I'll go ahead and say, well, the activity coefficients are actually the exponential of what I had already calculated. I'll just reuse that activity variable just to make things a little bit simpler, and then I'll just return the activity coefficients. Sweet. So now if I run this, let's see what I get. Well, that looks correct, right? It's returning to me these activity coefficients now, and that's an array of the activity coefficient for methanol being 0.99, for ethanol it's 1.14, and for water it's 1.6. That is, that's the same as what I got down here. So sweet, with that I have done the part in Einstein summation, or I have calculated the activity coefficients using the NRTL model using Einstein summations, and next I'm going to finish off part 1 using matrix vector multiplications. So I'll be back with you for that. I'll be back for that in a few minutes. All right. So let's continue on and take a look at solving the NRT activity coefficient model with matrix vector multiplications. So let's go ahead and maybe take what we did in einsum and copy these first few tabs, make a new function, and instead I will define this as maybe matvec. I don't know. I still want to give it mole fractions. I still want to give it a temperature. I still need to take those same properties that I was using before. I disconnected the runtime because it's been a few minutes, so I need to restart that runtime. And then I probably need to go through and run everything sort of independently once it all gets going. Connecting, it's just doing something. I'll go ahead and start working on this function, I guess. So what is matrix multiplication, right? So let's look at maybe this example up here, what I've been calling term 1 this whole time, right? So we have the mole fractions, which is a 3 by 1 matrix. We have tau, which is a 3 by 3, g, which is a 3 by 3, and that's of course because we have 3 components. And then we can multiply these together, or do a matrix multiplication so that x is multiplied and then added to all of the values of tau, g, so tau and g multiplied together in a row. So I think a good place to start out would just be saying that term 1 is going to be equal to it's going to be equal to x matrix multiplied by tau and g just multiplied together. Tau times g. So this is just a regular multiplication, so this will just take like the 3 by 3 matrix that is tau, and then multiply that by all the values in the 3 by 3 matrix that is g. So it's just sort of value by value. But this matrix multiplication is going to say the x is a 3 by 1, and it's going to match, like, there's going to be the fraction of methanol is going to be there for a certain tau, the fraction, or for the certain thing of tau g. And yeah, so this is going to like automatically add all this up and compute what we want to compute for this term up here. So then we can come down to term 2, and term 2 is just likewise going to be x matrix multiplied by just g this time, because that's all this one was. And so then we can go through, and then we can say, sticking with the same notation as before, part 1 is going to be, what's it going to be? Well, it's going to be term 1 divided by term 2. And then let me go ahead and print, if I can spell, which I can't, print part 1. And then maybe go ahead and call the function down here after that in the code, if I can get it without the colon. Run that real quick. Oh, and I haven't ran all the stuff I need to run yet. That's a silly mistake. Run that. P still isn't being run. Oh, I haven't run any of the code yet, have I? I need to run the imports and installs. It's going to take a minute, I'm sure. We'll see. Oh, it's doing a lot of stuff down here. Sweet, took 3 seconds. 3 seconds is a long time when you're making a video to be doing nothing. So now if I run this, now I get those basic things, and now I should be able to run this one. And yeah, sweet. So it's saying part 1 is these 3 values for the activity coefficient. And if you look at any of the stuff I've done, maybe I'll unprint that and then run this one. And yeah, sure enough, you see down here, look at all that. Those values are the same. So that's great. Going back up here, loops, einsum, matrix vector multiplications. We'll go ahead and close out einsum and loops. So we've done it correctly so far with this part 1. How do I do part 2? Well, similarly to what I did when I was calculating the NRTL activity coefficients using einsum, let me go ahead and solve and figure out what's in this parentheses first, and then I'll sort of multiply that in with this. But remember, ultimately, the main matrix multiplication I'm going to be doing is a 3 by 1 xj matrix multiplied by everything else, which should be a 3 by 3. Now, an important note is that you look at the way the axes are. Before, I'm doing a j multiplied by a ji. This time, I'm doing a j matrix multiplied by an ij. So I actually need to change the axis by which I'm multiplying this. And what that means is that I'm going to have to take the transpose of x and then matrix multiply that with whatever. Or actually, no, I'm going to need to take whatever I'm doing and then matrix multiply that with x dot transpose. So instead, I'm multiplying a 3 by 3 by a 1 by 3 in this x. So yeah, sweet. I think that that should all work out. But how do I do this math? Well, what's in the parentheses over here? This is just tau minus minus what I did in part 1, right? So I can go ahead and maybe make some parentheses. Already did. It made both parentheses automatically. So I can just say that's tau minus yeah, part 1. But similarly, I need to broadcast, similarly to what I did in einsum, I need to broadcast by the first one. So I will broadcast relative to the first axis. So tau minus part 1. Yeah, so that's pretty sweet, right? And then I need to come in here, and I need to say that we have, let's see, what am I looking at? Yeah, so we have what's in this parentheses here. I need to multiply that by the g, which is a 3 by 3 matrix, because this is a 3 by 3 matrix. And then I need to divide it by this this matrix right here, which would be a 1 by 3, so I will need to broadcast that by another axis. So I can maybe start out by multiplying it, so g and times that, and then divided by part 2, or yeah, term 2 rather. So term 2 is something I've already defined, but I need to broadcast term 2 because term 2 is a term 2 would be a 3 by 1 here. I need to make that, I need to broadcast that out so that it can be multiplied into a 3 by 3. So I'll just do the same thing I did before with this part 1. And then put that all in parentheses so that way it can all fit together, those two parentheses meshed up. So now I believe that I can comment this out, and then I can come in here and I can say that the activity coefficients are just going to be equal to part 1 as I've defined it plus part 2, 2 as I've defined it, and then of course say that the activity coefficients are actually the exponential of what I just did. And then I can just go ahead and return that. Sweet. Sweet. Okay, so return the activity coefficients. Yeah. So this is what I've done so far. Let's go ahead and run this and see what I get. Sweet. So the activity coefficients I calculated via the matrix factorization is going to be the same as what I got via the einsum, which was the same as what I got using the activity loops. The best way to do things is probably for most matrices is for mixtures of fewer components is just going to be this activity matrix vectors using matrix and vector multiplication. I think that's just the most straightforward, and once you understand the concepts, easiest to program. Kind of the worst way is definitely to use loops. It's simpler conceptually, but having to write out all that math is pretty time consuming on you, and then also pretty time consuming on the computer. So yeah, with all that in mind, have I answered all the questions in this part? I compared the results for all three for an equimolar mixture of methanol, ethanol, and water at 300 degrees Kelvin. Next up, I'm going to be moving on to part 2 and talk about calculating the dew and bubble point temperature using the NRTL activity coefficient. But with that, I will end off the video for here. Thank you very much for watching, and I hope you have a wonderful day. Bye-bye.